oscillation in a holographic repeat.
Okay, thank you very much for the opportunity to speak here. I'm going to talk about magnetic oscillations in a particular holographic liquid. I guess previously I had given the title Magnetic Oscillations in Holographic Liquids, but this is really going to be only one that I will study here. And it is a pretty crude one at that. So this there are very crude approximations that I'm going to make, and those will be apparent as I get to them, and there are many improvements that can be made. Now, this is work that we've been working on with Valentina Giangreco at the University of Iceland, Sean Nowling at Jamestown College in New York, and my former PhD student Tobias Zing, who's in Utrecht. And I will also review some older work that we did on related subjects. Okay, so this falls under the sort of general rubric of applied ADS-CFT, which by now, as you all know, has a growing list of applications, where basically we are taking advantage of the ADS-CFT correspondence to learn something about some strongly coupled quantum field theories, that is, those who have or are assumed to have a gravity dual, and whose parameters, in particular the coupling, is strong enough that you can work with classical gravity. And the particular system that I'm going to be looking at is a quantum critical system, and we want to apply this to study well, we hope that some of this may have some application to systems that involve strongly correlated electrons, and in particular, that hope can at best be realized in 2+1 dimensional systems, so that is what we'll focus on. Now, this is very much in the spirit of what's called bottom-up approach. That is, you construct simple models, as simple gravitational models as you can get away with, to see some interesting structure. And then, if you find sufficiently interesting structure, then you would be motivated, and I would say only then, should you be motivated to go and do the harder problem of embedding this into string theory, where you can really hope to have a well-motivated ADS-CFT or generalized ADS-CFT description. And so our approach will be that the gravity model that we write down is dual to some strongly coupled quantum field theory. We will use the ADS-CFT dictionary to calculate correlation functions for this quantum field theory, or actually today I will mostly be focusing on doing thermodynamics, so I will use the prescription to compute thermodynamic potentials and look at their behavior, in particular as I vary a background magnetic field. Now, so in order to get interesting behavior, I will couple this system to gauge field, U1 gauge field in 4 dimensions, and also throw in matter in the form of fermions in the bulk to get at the physics that I'm interested in. And sort of on a general note, when you do this, the back reaction due to this matter may not only influence the infrared behavior or the near horizon geometry, if you like, once we're doing this at finite temperature, it can also modify the asymptotic of your away from ADS space, and this can be very useful for if you want to study, for example, non-relativistic systems, which are, of course, typically what you have in condensed matter physics. But that's not where I'm going to be going today. I'm going to stick with asymptotically ADS models. Okay. Now, all right. Just keeps going. Yeah, okay. All right, how many do we have? Very good. If there's a lot of this going on, then maybe it shouldn't be so frightening, that number that shows up, how many slides I have. It's presumably quite a few of these repetitions. Okay, so what I'm going to focus on are quantum critical points. So let me just remind you a few things about them. So these are occur in systems where if you have some, you can vary some control parameter. It can be strength of a coupling, it can be magnetic field, external pressure, where your system, the ground state of your system, undergoes a qualitative change. The ordering in your ground state will change, and what I'm interested in are continuous quantum phase transitions, where basically in some characteristic energy scale, the gap between your ground state and some excited states is going to zero with some power law, and at the same time a coherence length is diverging, so that you have scale symmetry here. And generally you don't have to scale the same way, so you can have what's called a dynamical scaling exponent. Now in the systems that I am looking at today, this exponent is going to be set to 1 in the underlying short distance physics, but we will see, although I'll not go into it in any detail, that this type of scaling behavior can occur can emerge in the infrared, in these electron star geometries that I'm going to look at. Okay, but this being a scale invariant theory, once you turn on temperature, you will find that if you do that exactly at the critical point, the temperature is going to be the only scale in the problem. And in order to get something more interesting to work with, you have to deform away from the critical point. And so if you have some parameters that do that, you still will find that in this quantum critical region, the physics is governed by the point, by the critical point, and that manifests itself in that your coherence length, for example, will satisfy some rather simple scaling properties. The overall scaling will be determined by the temperature, and then there will be some dimensionless combinations here. You'll have some scaling function that you are then interested in computing in each case. All right. Now, as I mentioned earlier, physical systems with various different values of Z are known. You can even have non-integer values or non-universal values. The case that I will be focusing on is when Z is 1. That is when this scaling symmetry is actually part of a larger group, a conformal group, in which case your geometry is asymptotic to ADS. And I think in the following talk we will hear about geometries where you go away from this and you actually can have scale invariance without conformal invariance. Okay, so I'm going to go and my starting point is going to be ADS spacetime, and then I will generalize that in various ways. I want to discuss finite temperatures, so I want to be able to talk about systems that have, the way I will approach that is by introducing periodic Euclidean time, standard approach. This, of course, will introduce an energy scale. As I said before, you'll break your scale symmetry. And on the gravity side, we achieve this by studying a black hole configuration with a Hawking temperature, which we identify with the temperature of the quantum field theory system that we want to study. Under the ADS-CFT dictionary, if you want to study a system that is at finite charge density or finite chemical potential, you basically add a charge to your black hole. And if you further want to have magnetic effects or background magnetic field, you can actually also add rather economically, you can add basically have it be magnetically charged under the same U1. And then we're going to throw in some matter, and this will be charged under the U1 of the bulk theory. And depending on the type of matter, if it's scalar, charged scalar, you'll get a holographic superconductor. But what we want to focus on are when you put in fermions into the bulk, and we want to sort of look for evidence for a Fermi surface in that system. So you want to study the Fermi surface and properties of it in the dual theory, in the dual field theory, but for that you need to have finite charge density, and of course this has previously been studied in a lot of detail by coupling probe fermion to the box system, and I don't want to do that. I want to look for some sort of intrinsic properties of the system that I have and study those and see evidence for and of Fermi surface in that way. But I'll comment on that more as I go along. Okay, so I've sort of gone through this already, but let me just define some notation here. So starting point is ADS space-time, and then we will consider static black hole solutions, and these will be planar black holes. So horizon is planar, and then if you want to add the charge density, you put chemical potential into your background, and that gives you the ideas Reisman-Nordström. And then if you want, you can also add a magnetic field, and that slightly generalizes your solution. And then, as you know, if you to study sort of the low energy behavior of the dual field theory, you are interested in the properties of the geometry that are far away from the asymptotic region, so the deep interior here. And depending on what you have there, you're going to get, you may or may not get some interesting dynamics. All right. Now, if you do this at zero magnetic field to start with, you a reference system is where you have just an ADS Reisman-Nordström black brane. So then the charge, so charge density is dual then to electric flux that comes out to infinity, and that is sourced by something that sits inside the black hole. And then an alternative is if you have some charged matter in the system, and you can find configuration. For example, if you have a scalar field, you can have a black hole with scalar hair, and this has of course been studied in holographic superconductors. And then you can ask the question, which, if you have these solutions to your system, which one is thermodynamically favored? And what you find is that at high temperatures you only have the ADS black brane, and then as you lower the temperature you find that there is a branch which is the holographic superconductors. That is, these are the hairy black branes, and they actually have a lower free energy than, and there's a phase transition here which is a continuous second order phase transition. And in the system that I'm going to be looking at, which is the so-called electron stars, you have a very similar picture, except that the transition is actually in the Thomas Fermi approximation that one is using there is of higher order. It's a third order transition, which is an artifact of this approximation for sure. And but let me get there in a minute. Okay. So. So we're interested in systems that have that exhibit metallic behavior, but perhaps some non-standard behavior. And so what we're going to do is we're going to add to the system, rather than a charged scalar field, we can add charged fermions. Okay, and this has been done at the probe level by a number of authors. So where you ignore the back reaction on the geometry due to the fermions, and this led to very interesting results. So you basically adapt your ADS-CFT prescription to this setup. You solve the Dirac equation in the bulk. You look at the behavior of your fields as they approach the boundary. Those will act as sources for some fermionic composite operators in in the dual field theory, and you can study their correlation functions. In particular, if you compute the 2-point function, you can read off from that the fermion spectral function, which can in fact be more or less directly compared to some scattering data that you can obtain in experiments. So this is and you found some rather intriguing behavior. So going through this procedure, depending on the parameters of your model, so basically you have some parameters here. You have the mass of the fermion, for example, to play with. You will find that your 2-point function will have poles, and in particular, so those are, if you have a sharp pole, that's an indication that you have a Fermi surface in the system. And depending on the parameters, the nature of these poles it can be different. But and if you this parameter nu here, which depends on the mass and the charge of the fermion, if this is larger than a half, then you will have this width here of the pole will be small enough that you would say that you have long-lived quasi-particles. And in particular, if you were doing standard Landau Fermi liquid theory, this would actually go like omega squared here. So nu would be 1. If it's less than this, then this is too broad to really think of it as having stable quasi-particles. And then there's this interesting dividing line which has a log suppression of the residue of the pole, which actually matches rather nicely onto some phenomenological models that people have studied in condensed matter physics that are called marginal Fermi liquids. So this is a story that has been told, and I'm not going to go into it in detail. But what I want to think about is how would you now go beyond this probe approximation and really study the system with these fermions in the bulk, but and taking into account the back reaction on the. Now, of course, at first sight, this doesn't seem like a very good idea. You started with a strongly correlated system of fermions in 2+1 dimensions, and then you've moved up 1 dimension and you've gone from flat spacetime to curved spacetime, and now you're going to try to solve a system of coupled fermions there. And so there are, and this is true, this is a difficult problem, but there are some inroads that have been made into it. And in particular, this Thomas Fermi approximation, where you treat the fermions as a continuous charged fluid, has the nice feature that it's manageable and you can do calculations. It is perhaps not necessarily a very good approximation to the system that in fact, it's almost certainly not a good approximation to the systems that you really want to study, but you have to start somewhere. So I guess we can acknowledge that we are guilty here of sort of looking where the light is, that is, we are going to do calculations in the system where we can actually do them, and hope to learn something useful and get some hints and indications as to how you would want to proceed beyond that.
I thought one of the punchlines of this recent work by John McGreevy was that this is an astonishingly good approximation to the exact result. You've got no reason to trust it, but it's just very, very close to the exact number.
Spending, right? I mean, it's spending the parameters whether you get out this infinity of Fermi surfaces. As a physicist, I'm not interested in that. It's a variable charge.
Look,
all hell breaks loose.
The back reaction on geometry, I think this just gives the right answer even in regimes of parameters.
Right. This may be, but then of course.
No. At some point you're doing physics or uncondensed matter.
I think there are.
But your boundary system has all these Fermi surfaces, and of course that's of importance for the surface.
This is a large n-ish.
This is a large.
No, it's about a fermion charge. It's about a fermion charge, not large n. The fermion charge really. So what you do is, it's a weak correspondence, right? At the moment you see these fermions in front of the horizon, it's weak, and then you tune up that charge and you find out that the Micinos you described in the boundary field theory gets less and less degenerate. And then I can ask, what the heck is there in large n theory right? That these masses of these machines have to be all together. Right, you can just tune by the charge independent of large n, these machines masses be quite large, ending up with sort of single Fermi surfaces.
Well,
And the case in point is really the thing by Subir where he has the hard wall, right, and then you get a very clear view on what the physics is out there.
but even better if it's a good approximation. I mean, I was simply, my apologies were simply that this was the only approximation where I have been, where I've done this calculation. I think if I were, and I think it's a very interesting thing, is to go beyond it and study it. And also, of course, it depends on what you're calculating, how good a picture this is going to give. And so, I'm certainly interested in going beyond it, but that's not. This is what I have studied so far. And I think there must be certain things that this cannot capture. For example, in this approximation, in this electron star, there's this sharp boundary here to the, and so the bulk fields don't make it out to infinity except the long range fields, and I think you are bound to be missing some things there.
So I also want to emphasize work in light and light fiction.
It's That's
you can do that WKB mild equalization, and actually into a degree, I agree, right?
Yep.
I'm
going to suggest.
You have to attach long tails, right, so that you extend the wave function to the boundary. That is a detail.
Sure.
The bigger deal is that by WKB you find out that actually that third order transition is limited to first order transition.
Absolutely. I was
Find a sort of weak singularity.
This is all coming up, and in fact, one of the things I will suggest at the end, that the natural way to extend this work is to then do the corresponding computation as they do, using WKB wave functions, except including the Landau levels now with the magnetic field when I have them in. But anyway, we'll get there, maybe. Okay, so we're going to then make this approximation. We're going to treat them as a charged fluid, and we're going to see what we get. And what you get is known for the at t equals to 0. It was worked out by Hartnell and Tavanfar, building on earlier work from these papers, that you get a rather nice picture. It's a charged fluid, and you will find that it changes the infrared behavior of the system away from the ADS black hole. Basically, the ADS black hole is unstable to releasing its charge to this charged fluid outside, and you end up with at 0 temperature you have a system which does not have any black hole horizon, but it has actually an emergent Lifshitz theory, emergent region in the infrared where you have Lifshitz scaling with a dynamical scaling exponent that depends on the parameters of your fermions. So let me outline how that works, but before I do that, just give you so we have, in this system, we have the gravitational coupling, so this is basically Newton's constant, and we have the electromagnetic coupling. And for this fluid description to work, you want these to be weakly coupled, both the gravity and the gauge field. And furthermore, you want the Compton wavelength of your fermions, your constituent particles, to be short compared to the characteristic length scale of your geometry, and that I was calling lowercase l before, and now it's become an uppercase. Sorry about that, but and it'll be most of the, or at least some of the transparency. So let me apologize about that in advance. Also, I'm sort of going back and forth on that, but. So the equations are standard. You have the Einstein equation, you have the Maxwell equation, and then you have the energy momentum tensor due to the Maxwell field. You have, by assumption, you're going to have just the standard fluid description, but it's now a charged fluid, so it acts as a source for the Maxwell field as well. And in order to get a system to solve, you have to, of course, also get some equation of state for this fluid, and there we will make the assumption that this is a degenerate gas, in the local Lorentz frame, and this is motivated by the fact that this thing has a quantum wavelength that is small compared to the scale on which the geometry is varying on. And then we simply put in an ansatz for our metric, or write it here in terms of the tetrad. And then my ansatz for is that the time component of my gauge potential is a radial function, and it's convenient to take a look at, include the appropriate component of the appropriate tetrad component, so that the local chemical potential, which is going to be very important for the physics, is actually given in terms of this ansatz simple function A here. Okay. And then furthermore, to simplify the notation and also to be able to put this on a computer, one scales out the various dimensionful couplings, and so those are the hatted variables. And finally, you simply assume that you have this dispersion relation for the fermions, and you fill up the states. So if your local chemical potential is larger than m, then you can start filling up, and then you will have a Fermi surface at where the at mu, and then you simply calculate a density of states in the standard way, and you end up with this expression for the charge density of the fluid, and you have this is the energy density, and then pressure will be then given by this thermodynamic relation, which holds locally in the bulk. Now, you will notice that I'm using a degenerate gas, which means I'm actually taking the temperature of the system to be zero in the end. This is of course fine when you're doing this at zero temperature, but eventually I want to go to a boundary system that has finite temperature. But I will actually still stay with this approximation that I'll take the bulk temperature to be zero. Basically, the thermalization that you would expect due to Hawking radiation is going to be, it's a quantum effect and will be suppressed by some power of 1 over n, and I will ignore it. So that's one of the approximations I'll be making. Okay. So now I want to generalize this to finite temperature, and then I want to generalize it to a finite magnetic field, and the magnetic field will be sort of pointing in the radial direction, so that it's transverse to the two-dimensional spatial slices that I'm interested in. Okay. Now, the generalization of the electron star to finite temperature was worked out simultaneously by our group and by Sean Hartnell and his student back in 2010. And it's so, as I've just said, I'm not going to put a finite temperature into the bulk itself. The way I'm going to get a temperature is in the usual way in ADS-CFT. I'm going to have a horizon with an associated Hawking temperature. And so the construction starts with a charged black hole. Then, as I move away from the horizon of the black hole, in fact, the local chemical potential is just to have a single-valued gauge connection that requires the local chemical potential actually to vanish at the horizon, which means that the fluid cannot be supported there. And so it then grows away from the horizon, and if it at some point you satisfy this condition here, that the local chemical potential becomes bigger than m squared, then you will find that you start having a fluid. And then as you go asymptotically to infinity, the local chemical potential also vanishes, and so that there must be an outer edge to this fluid. And this outer edge, of course, it has in common with the electron star. The new feature here is that there's an inner edge as well to the fluid.
This is the solution to which equation?
These. Okay. And so the only solution you have close to the black hole is the one where this is zero.
So you don't backreact on the black hole?
Yes, you do. No, you do. let me go through it in a. I have. The construction is you start here, and once you get to this point, let's say you go. These are translation invariant and rotation invariant in the plane. So the only and static. So you're only really integrating in the r direction. And you start here with your black hole. You have an exact solution up to this point that the fluid turns on, and then you use that solution as an initial to give you initial data in a numerical integration of the equations with the fluid.
So is it discontinuous at that point?
I'll show you. It's continuous, but there are some derivatives that will be, some.
It's like putting some wall there in some sense.
Well, it's like putting a cloud of electrons, and it's one of these things that we were referring to before. There is a sharp edge to this. But it's not discontinuous, and I think the charge density is, it's differentiable, but not twice differentiable. And so you will see some funny features in my final results due to that. There are some kinks in some plots, and those will be smoothed out once you go beyond this.
But it's demonstrated by Kubovich, etc. in the publication.
Yeah. So that's certainly one very explicit way of saying that you have to go beyond this approximation.
Marut?
Yeah.
To check, so near the black hole, the geometry is identical to what it would have been without the electrons.
This is simply I choose to look at a solution where I start with some black hole with a charge. I will then integrate my way out. I will find that the fluid starts developing, if you like. And this is what we call, and then you will integrate further out, and eventually you will run out of fluid. And from then on, it's again the vacuum. And so it must be again some black brane solution, but it's not the same black brane. The parameters are different. And so in that sense, you've back reacted on the geometry that your asymptotic parameters are not those of the black hole that you started with in the interior. Okay? And
There's one or two discontinuities as you go up.
two.
And the star is
Let me show you the result actually. So here is what you get. You start with. So, okay, our notation was slightly different. U was log of r, and so you're moving minus log actually. So you're coming in from the horizon here. Sorry, from the boundary, okay? R is 0 at the boundary. This is where you have your Reisman-Nordström black brane. You then start integrating numerically. This is your charge density, this is your energy density, this is your pressure. And I think this guy comes in with, I think it's U to the 3/2 or something like that is the behavior.
There is no charge density at the boundary?
Nope, that's a problem. But it's
That's
the
all
only
right,
thing
yeah.
the only thing you have at the boundary is the gauge field due to that charge density. You don't. So the matter fields, the wave functions, if you like, of the fermions they don't extend. So
So again, I advertise the work by Kubovich.
yeah, I will do that also.
And for replace all these problems.
Right.
But
But it's a more complicated calculation than the one I'm going to do. So that's why we haven't done it yet.
I mean, if you hadn't been doing this fluid approximation, if you had real fermions,
Yeah.
there would have been normalizable modes with some appropriate
Presumably.
fermion bilinear
Yes.
1 point function.
Yep. But
But you don't see it in this.
don't see it in this approximation, no. That's of course is a somewhat non-trivial thing to do.
But,
again, I mean, Kubovich solves that. Right, exactly the thing that you go leading order compensation. Right, and a sharp edge of the star disappears. Right, so the waveforms extend to the boundary. And so that the big effect is, right, so you have this halo star, you have the black hole in the middle, and this halo of electron matter around it. And at 0 temperature, right, that really goes all the way to the deep interior. And you do the classical star. You requantize it and you again recover that there's a little hole in the middle. And that explains that the short order transition turns into first order.
Yes?
About the geometry, so what is the gap between the horizon and the inner edge of the, I mean, can you make that arbitrarily small, or?
Well, it depends on the mass of the fermion. If the fermion mass goes to zero, it actually shrinks away. Because the condition was very simple. It was just that you can only have a fluid if your local chemical potential is larger than m. And the local chemical potential will necessarily vanish at the horizon. Now it is also, you also have solution where it never makes it to this. And those are the high temperature solutions where you only have the black brain all the way out and no fluid at all. And we'll see.
Something. The reason you take this discontinuous solution is to have something analytic. Is that correct? Solve it numerically.
I could have solved it numerically.
That's different.
No,
That's what I'm trying to understand.
I could have solved it numerically, and if my numerical integrator was any good, it would have tracked the exact solution.
That's what I'm trying to understand.
Yeah, absolutely.
Okay.
But it seemed
And
more
this
efficient to.
is happening because you chose a Reisner-Nordstrom horizon. If you chose another horizon, it could have been different.
Well, if I chose one, for example, without a charge, I would never see anything because there wouldn't be
Not
any.
without a charge, but there are different types of near horizon geometries that one can use, which have different properties. For example, mu doesn't have to go to zero.
That's true. That's true. But this again was sort of the minimal in the spirit of the bottom up. You take the simplest model, then many ways to generalize. Absolutely. Yes.
Is the system on the boundary in thermal equilibrium? And
That is yes.
what temperature?
At the Hawking, we'll come to that. It'll be a Hawking temperature, but it'll be dressed by the effect of the geometry comes through. It's dressed by this function here, which is, of course, if you're just doing the original Reisner-Nordstrom solution, it is actually 1. The tetrads are inverse to each other. But once you've done your fluid integration through the fluid and you match onto the exterior Reisner-Nordstrom, doesn't have to satisfy, it doesn't have to have a smooth horizon because that solution doesn't apply all the way up to the horizon. So that means the C here will be different, and what you will get is that it doesn't it evolves as you go through the geometry, and then it freezes and it's constant in the outer geometry, but that constant comes into the, so it's a Hawking temperature divided by the asymptotic value of C. We'll see that in a minute. And this is actually important because that is how you get to zero temperature. It's this factor, the C here is actually diverging. It's not that you're going to an extremal black hole on the inside. Okay? Well, we're still in 2010 here. So let's move on. And now let's see. Let's discuss this solution a little bit further, and just to make sure that we had understood it properly, we did the thermodynamics. We found that this electron cloud, as we call it, sort of we view this as you start with the horizon, then you move up from the horizon, and then you'll find this cloud of electrons that are suspended above this horizon. They're basically, you balance the gravitational attraction with the electrostatic repulsion, and then you can do various calculations here to see that you've sort of got things working correctly. So first of all, you do the thermodynamics, and you see that this is of course the electron star, and we had already said that that's favored to the extremal Reisner-Nordstrom, and this is a high order continuous transition. But as Jan has mentioned, when you improve on this and you do better modeling of the bulk fermions, you will find that this is actually a lower order
I will
transition.
put it differently. So the H bar between the limit is just a single limit. So
Yeah.
you will always have a finite H bar,
Yep.
right? And for any finite H bar response disappear. With
Yep.
very mild singularity.
Yep. And then just to make sure that we were not sort of that our formalism was working, we actually checked that you could compute in a standard the AC conductivity, and it sort of, this is what you get for the black hole, this is what you get for an electron star, and our cloud sort of nicely interpolates between the two, as you would expect. Now furthermore, you can see how this is what I was mentioning before about the interior black hole. You might expect that as you go to zero temperature that you would approach an extremal black hole in the interior, but that's not how it works. It is that the dressing of that temperature gets larger and larger as you go to zero temperature. And actually, you'll find that there is this gap in between here. And this is very straightforward to understand from the gravitational point of view, which is because gravity is attractive, there's a focusing effect, so that if you try to start your numerical integration based on something closer to an extremal black hole, what you'll find is that the fluid outside will actually focus your geodesics in such a way that there's a singularity before you get to infinity. And so there is a restriction now that you have to put on your initial data. You're not allowed to start with a value. So this is basically the charge parameter of the black hole extremal. This q squared is 6. This is the interior guy. If you try to go to these high values here, you'll find that your integration will lead you to a singularity before you make it out to infinity. So basically, this is the range that's allowed for these guys. All right? Now, and what happens is actually that if you now go from the outer edge and in, you find that if you take a look, for example, at the Ricci scalar, which in the ADS space and the units I'm using, it will have the value -12. And this is the value for the particular parameters here that you would get in the deep interior of the electron star. So that's the Lifshitz. Lifshitz spacetime also has a constant R. And you find that you sort of approach that as you go to lower and lower temperature, you approach this value. And then, of course, when you go far enough in, this solution, of course, does have a black hole in the middle, so this thing will drop down. But so this basically is the interior of the electron star. So we're recovering that rather nicely. And in fact, you can also recover by seeing how this distance here depends on temperature. You can see the Lifshitz scaling, and with the correct scaling exponent. So I'm not plotting that here. All right. So these were the electron clouds, the finite temperature. But now we also want to include a finite magnetic field. And then life gets a little more interesting. So now we're going to start with a dionic black hole, which has a background magnetic field. But we now also need to think about how the fluid reacts to the magnetic field. And so to do that, you have to study a more complicated system. And so if you want to do it in full generality, you need to do sort of magnetohydrodynamics. So I'm writing here the field equations for a general charged spin fluid. These have been worked out by astrophysicists some decades ago even. But it turns out that I can simplify things quite a bit. Just for the effect that I'm looking for, I'm going to ignore sort of the spin G factor of the electrons. So I basically treat them. I will put the spin G factor to 0, which means that my spin up and spin down, the magnetic field will define a direction. The spin up and spin down will, in general, behave differently. But if I put the spin G factor to 0, I can just treat the fluid as a sum of two fluids of up and down. So that certainly simplifies things. I will also assume that I have translation symmetry in the plane and rotation symmetry, and that further simplifies this Lagrangian, so that many of the terms in these energy momentum tensors actually drop out. But the minimal thing that I will need is, now I will have my local chemical potential as before. I now will have a local magnetic field, which, because of the, if we go back to the, or maybe I can go forward even. Yeah. So my tetrad has the usual redshift factors that you have in ADS. And so that means that the local, even though you have a constant B field in your background, the local magnetic field actually is position dependent and gets stronger the closer you get to the black brane.
Do you have any clue what meaning is in the boundary of setting a spin G factor to 0?
Well, it's clearly, I don't know of any real fermions that have that property. It was just to simplify the system. What happens when you have it non-zero is that your formulas get more complicated, but I mean your Landau levels will be split, right? The degeneracy of the
It's
Landau.
like a Zeeman splitting.
Yeah, I'm just turning off the Zeeman splitting. That's all.
Okay.
I only want to have orbital magnetic effects. That's just to yeah. It turned out the numerics was hairy enough.
Can you comment on this? All terms in the stress energy tensor. You have T of the electromagnetic part and the fluid.
I have that. I have, and then this is the that sort of will be the charge part of the fluid, and so in the approximation that I'll make, this part will reduce to just this standard one that you're used to, okay? But in general, it can be basically what these equations do is they allow you to study a system where your frame of reference, your local frame, is actually a dynamical variable, a part of your dynamics. You don't really need that for this system because we're going to study something which is static and only with radial dependence. So, but that's what this will do for you. This is the magnetization, sort of the response of the fluid to the magnetic field. And that again will also simplify considerably in the system that we're going to look at. It's only going to have a couple of terms, but it's sort of the term is of the order that you expect. It's a B field, sort of an n times B interaction that you get there, and then finally you have the usual fluid thing, and then these are spin. These are things that come about due to the spin, and you can, and also if you allow your particles to carry an internal energy, that's where you get this term. But since they will drop out in the particular thing I'm going to look at, don't want to spend too much time on them. But the nice thing about this formalism is that you can certainly, it is flexible enough to study more general questions than the one that we were focusing on.
What is epsilon?
Say again?
What's epsilon? What's capital epsilon?
It is if I remember correctly, it's an energy density that sort of comes from the spin degree of freedom of the particle. So it's something that's allowed by the symmetries of the most general problem to have it around, but
You're just splitting up the total energy density into those two components.
yep. Well, I shouldn't say this was done by Israel and others sort of back in quite some time ago. And by Schutz, I think, also contributed to this. Now, we're going to do the same game again. We're going to assume that we have a degenerate gas in a local Lorentz frame, but this time our particles will have a piece that comes from their orbital motion. And so these are local Landau levels in the bulk, and it's really, that's where our effects are going to come from. And what we need to do is to sort of translate that local physics in the bulk and see if it actually adds up coherently to give you a contribution of the boundary, or whether things wash out. Because in some other computation you do in this model, you find that even though you have effects in the bulk, they don't necessarily result in the corresponding effects on the boundary. And what I have in mind is calculation we did where we studied Friedel oscillations in these systems, and we found that for the electron star, this is in the absence of a magnetic field, even though you had clearly Friedel oscillations in the so these are these 2kF oscillations that you expect to see if you do density-density correlation functions at finite momentum transfer, and when it is commensurate with crossing the Fermi surface, you expect to see some non-liticity in those correlation functions, and we found that those washed out in the when you computed, when you added up the effect of the different radial positions on the
Just that you have all these different Fermi surfaces.
exactly. So the question was, are you going to get the same?
The way it's physical.
Are you going to get the same thing here, or are you not? That's the question. And of course, the answer to that question is going to be no, because otherwise I probably wouldn't have had you all sitting here listening to the talk, and we actually do see an effect. But well, I think it's interesting that these two different ways of probing the Fermi surface are giving you very different answers in this model. Okay, so the formulas are going to be a bit, even with these simplifications, are going to be a bit more complicated than they were before, but it's basically the same thing though. You add up, you start as soon as you have your lowest Landau level is allowed, you start filling it up. But then if your local chemical potential goes higher up, then you can also fill the second Landau level. And then, so you will have this multi-fluid picture, if you like. You will have the leading order, you'll have the lowest Landau level, then you will have the second, third, fourth, and you basically have to add up the contributions of those. And so this is what we'll do. The number of occupied Landau levels is going to come from just the condition that your energy be sufficiently high at k equal to 0 to at least allow you some. So that's where you get this from, and this is going to be something that depends on your radial position. It'll be negative very close to the dionic black hole because the chemical potential is not high enough. But as soon as it gets to 0, so this is basically the highest integer below the actual value of this thing here. That's what this symbol means. And as soon as you can start occupying Landau levels, then you will have to do the same thing as before. You have to take your dionic black brane solution, you have to start numerically integrating, but now your numerical integrator has to be mindful of that there's going to be a second threshold when the second Landau level comes in, and then the third and fourth. And you want to do this at low magnetic field where you have lots and lots of Landau levels. So this is why the numerics is slightly tricky. But in order to do this, you need
It should be something like this. You have somehow the field has to be small compared to something in order to be sure that you can use the fluid limit.
Well, let me just show you what we get, and then you see that things break down sort of where you expect them to break down in the computation. But anyway, so in order to get the equation of state for you, this basically you get the charge density by filling the Landau levels, and then you use the bulk local thermodynamic relations to basically you can integrate this relation to give you the pressure, and then you take a derivative with respect to the magnetic field to give you the magnetization density. And once you have those, you have your you can plug those into the Einstein equations and the Maxwell equations and see what you get. Okay? And so we do that, and so these are just the solutions to these. And now, again, our bulk variables are going to be the metric or the tetrads here. We're going to have a gauge field so this is the local chemical potential, but we're also now going to have a background magnetic field. And yeah, right. And this is the local field, and as promised, it's going to be R-dependent. So it actually goes to 0 at the boundary, and then it gets bigger as you get closer to the brane. Okay, again, you get rid of all the couplings by scaling your parameters appropriately, and then you make the simplification. With these assumptions, the right-hand side of the Einstein equation simplifies quite a lot. And you end up, nicely enough, with the first-order set of equations. And this, remember, was the C was this factor in the metric, in the time component of the metric. And you see that it actually is a constant unless there is so it's only in the fluid that it takes a change. So it is 1 when you start at the black brane. It then changes due to the fluid, and then it has some value at the outer edge of the cloud, and then stays fixed after that. All right. And then, well, if you stare at these for a little bit, you may be a little bit surprised that the magnetization density actually doesn't show up here. You seem to be able to solve the system without even worrying about it. And that's not quite true, because these guys come from the time and the R component of the Einstein equations. But if you do the spatial components, the XX and YY, you will find that those actually require this to hold. Or in other words, to see it is that this is the Bianchi identity. That says that the energy momentum conservation requires this. But this means that once you've solved these equations, you actually know what the magnetization is, the local magnetization. And then you have, I proceed as before. I start with this dionic brane here. And for convenience to do numerics, I use the scale symmetry underlying it to put the horizon at 1. All right? And then once I get to the point where this thing here, actually I start occupying Landau levels, I have to start doing numerics. And then at the end of the day, I match onto some exterior thing. And so these are basically outputs from my numerical computation at the outer edge of the fluid, and those tell me what my outside solution is. And once I know that outside solution, I can actually compute the free energy just using the standard story, and with the boundary counter terms so that's what I will do. And then to show you, I will show you plots of the boundary magnetization, which is basically given by this. Although because of this, of course, is a little bit non-trivial to do with these numerical solutions, but we have a procedure for actually obtaining this, which I don't think I'll go through in detail, but can talk about if you're interested. And then you'll see sort of a typical profile here. This is for a low number of I think this is 6 or 7 occupied levels. And you start seeing 1 and then another hump.
What is sigma?
Sigma is the charge density. So this is basically, you will have a profile for the first Landau level, and then you will have another profile for the second Landau level, third, fourth. Okay?
We solve this system exactly in the limit of magnetic field much, much bigger than chemical potential.
Yep.
Using bosonization. And we got things that wiggle.
Yep.
Maybe a bit more than that.
Right.
In your model, if you take that limit, does it start to look like what we got?
That's one of the things that we want to do. We haven't actually done a quantitative check. There's some funny things going on here because the weak field, we're more concerned about the weak field limit. I want to get to that. I guess I have 2 minutes, so maybe.
And the Zeeman splitting is crucial by the time you get to very large magnetic
Right.
fields.
So I think that we may have thrown that out with the. But all of this can be done with the Zeeman splitting in there, but it's just more hairy. And but if you're sufficiently motivated, I want when you're you may actually do it, or more importantly, if you have sufficiently clever people to do numerics for you, you may do it. All right. Okay. So let me just show you some results very quickly here. This is just to see that you can actually see how the Landau levels are filling. So what I'm showing you here is this is the temperature in the boundary system, the magnetic field here, and I plot this as a function of 1 over b. And you already see in this picture that there is a periodic structure, very regular, in 1 over b, which is, of course, what we're looking for. And this was not guaranteed beforehand. This is telling you is that you're not washing out you really are picking up. And furthermore, you can see that the limit where the magnetic field goes to 0 seems to make sense, because then all these Landau levels are collapsing onto a single fluid. And that's, in fact, I didn't tell you before, but if you take these expressions I have and you take the weak field limit, you can exchange the sum of over Landau levels with an integral. And if you do the integral, you recover exactly the expression that I had for you recover the equation of state of the charged fluid in the absence of a magnetic field. So that was just a consistency check, and sort of see that in this picture as well. This is sort of telling you where there is now going to be a phase transition again between if you increase the temperature, eventually you will find that there is no electron star anymore. But you can also increase the magnetic field and get the same thing. If you make the magnetic field stronger, even at 0 temperature, you will find that you lose the. Okay, you can of course recover it if you scale some parameters as you go with it. This is for
kind of potential effect. That this magnetic field, the energy quote unquote of the star is rising.
Yeah, that's right. I mean, if you increase the magnetic field, you basically you can't afford any Landau levels eventually, and it won't be because of the m squared. It'll be because of the other term of the lowest Landau. Okay, and then you can do an analysis of the free energy, and you will find that this is a second order phase transition in this Thomas Fermi approximation. Again, I expect it to be less, be a lower order if you do it in a. And let me just show you some results here. So this is for a, showing you here, M can basically range between 0 and 1 in this system. If you let it go to higher than 1, you never get any fluid. You basically can never then reach this condition to start occupying Landau levels. And this is a fairly low value, and you find that there's certainly oscillatory behavior here. Sort of interesting that the green dotted line is what you would get for just for the magnetization just for a dionic black hole. So that's sort of the reference we have. And you see that the sort of intriguing here is a little bit that you seem to, as you transfer to the black hole, but even before you get there, this is the phase transition point, you sort of go from on top of this oscillations here, you see a trend that you go from paramagnetic to diamagnetic as you lower the magnetic field, which we don't really have much of an explanation for. It's just seems to be a feature rather than a bug. And
It's just a diamagnet, it's not the orbital force.
say again?
Yeah, so when you have pure orbital magnetism, it always wants to be diamagnetic.
Right. So that's sort of, and when you, and that's right. So
makes a
you,
lot of sense. You're screening the field.
yeah, exactly, and you can do that more efficiently as you lower this. But now I plot this. This is for a higher value of the mass, so things track the in that case track the black hole. And you'll also notice that now I'm plotting for 1 over b, and there you really see that this is a periodic structure. But you also see, of course, because of our approximation, already at the level of the magnetization, we're getting kinks here. So if we were to compute the susceptibility, we would start getting spikes, which are artifacts of the. And also, of course, this is numerical solutions. The more derivatives you take off it, the less reliable your answer is going to be. Okay, let me just to show you that the period is this is exactly what you expect, that as you go to low temperature, this should stabilize, and then as you go close to the critical temperature, where you lose the thing, you find that you still have these periodic oscillations, but the period is getting larger, and then eventually sort of your numerics is giving out on you here. Okay? And that's really, I think, the last slide I want to show you. So this is sort of rather than to summarize what I've already said, this is sort of where would you want to take this from now? And so the basic question that we're talking about here is how can you want to learn things about the Fermi surface in your boundary theory from different points of view. And as I mentioned earlier, we've already gotten some very interesting story from fermion probe calculations. In particular, this has been applied to the electron star background in this paper here. I mentioned earlier that we've looked at Friedel oscillations, and those were where we did not see. There, actually, we found that the effect washed out for this electron star model, but we could recover it as a subleading effect if, for example, if you did Sashtev's ADS box story. And I think that you want to go sort of along those lines with this. I think you should be able to generalize. I think certainly this story here, that where you, instead of using the sort of this Thomas Fermi approximation, you basically play the same game as in Sashtev's box, where you, but instead of using the free wave functions, you use the WKB wave functions in this. And then you do an iterative procedure where you solve for the wave functions and the gauge field in a given background, and then you use that to solve the Einstein equations. And it's much more cumbersome than what I just did here. But I don't see anything in principle that would prevent us from adding a magnetic field to that story, and then we could compare that to the results that we have here. But I'm already over time, so let me stop here, and thank you for your attention.
Yeah, you know, I find it very interesting. I mean, we know, right, from the fermion probes, that in the fluid you have an infinite number of Fermi surfaces. You do the Friedel oscillation exercise.
Yep.
You know that you lose that Fermi surface information that shows up in the single particle sector, so to say.
Yep.
And now you find really genuine alpha oscillations that are no longer related to a Fermi surface. Right? You have an infinity of Fermi surfaces. Right, so it's a kind of a new way of getting quantum oscillations. It's very interesting. In a way, very non-Fermi liquid.
Right, but at the same time, we're still sort of, we can sort of understand where this is coming from in the bulk. It really is, there is a radial location which is dominating here.
It's just because duality.
Right. And of course, we haven't thought it through yet, but there's interesting questions to ask here about the Luttinger count, for example,
Yeah, yeah.
which I don't have an answer to at the moment.
You said that the magnetic field goes to zero at the boundary. So what?
The local magnetic field. Yeah. Remember, the local, you have in the solution, you have some background field, the magnetic field, which is acting as the source of your boundary magnetization. So there's a magnetic field in the boundary theory. And when you actually look at the geometry, you will find, because of the redshift factors in the ADS, that it is actually going to zero at the boundary. That's right. That's just a feature of the solutions. This is true already in just the dionic ADS black hole. It's not a new thing here.
Stability of this electron star. You studied stability. Are they stable configurations?
Well, they're thermodynamically preferred to the ADS black hole. We have not studied. No, we have not studied the GR stability of these black holes. Presumably they can't be entirely stable, because if you go to the zero temperature limit, you have this Lifshitz region in the interior, which has a singularity, which I think will be discussed soon. And that suggests that they cannot be physical.
You also might expect them to create translational.
Yes, absolutely. Right, yeah. And so we've not looked into that. All right.
Just ask the speaker again.